So it is a resource rational sequence prediction model as a model of sentence processing. So yeah, the starting point is so this is not the lab to where it takes work to convince you that language expresses recursive thoughts via linear strings of words, which means that we have some kind of recursive thought and we need to linearize this. And in comprehension, we do invert this kind of mapping from recursive structure to linear sequences, something that we do all the time, including just right now. But sometimes this can be very difficult, and that's what sentence processing is about in many ways. So I just wanted to do a quick experiment. So some people in the audience, of course, are very familiar with these things. Others maybe not so much. So we can just do a quick experiment similar to what we do with the humans. So a couple of sentences, and after one each, everyone can reflect, is a sentence grammatical or not. So start with this one here. The report was surprising. So I think there is zero doubt among anyone that this is an acceptable English sentence. And now it gets more complicated. The report that the doctor, who the lawyer distrusted, annoyed the patient. And now the question is this grammatical or not? And this is a very non-naive audience, but naive native speakers may easily be tricked into thinking that this is a grammatical sentence, but it's not. So as one can see, one verb is missing. So the report is missing a verb. So this is a kind of, it's an utterance, but it's not a sentence. So annoyed refers to the doctor and not to the report. So something is missing for this to be a sentence. And something like was surprising would make this complete. But actually, if we go to was surprising, then say the reading times on was would be elevated because people would be surprised to see the complete sentence. So that's, of course, this kind of forgetting thing that Shravan and your lab have been researching for a long time and doing pioneering work on. That's the classical finding. And one thing that we found, which kind of was sort of interesting, was that if we change report to fact, this gets much easier. Or we change annoyed to cured, it again gets much easier. So with cured, it's kind of clear that doctor and cured are a better match than fact cured. So that's kind of very sensible. But the fact that fact is better than report is maybe not so obvious. So we get this modulation of the center embedding difficulty by changing a few words. And that's really what this sort of study is about. Explaining, so understanding what kinds of modulations happen and explaining them with modeling. So yeah, there are the big question of sentence processing, when and where sentence is difficult to comprehend, and there are the expectation-based models like surprisal theory. And just for those, in particular from my own maybe group who are not familiar with this in many cases, I'll quickly go through this. So in surprisal theory, asserts that the processing difficulty of a word is proportional to the surprisal, which is the negative log probability of that word given its context. So the more unpredictable the word is, the harder it is. So here we have a high probability and a low difficulty, low probability, high difficulty. And this is sort of a classical account that's motivated in part by Gordon path effects. So, we have the horse raced past the bar and fell. And that's very confusing to anyone who encounters this the first time. And under the expectation-based account, the reason this is so hard to make sense of and so surprising is because, so it means this, the horse that was raced past the bar and fell. But it's very hard to get this reading, even as a native speaker. So the fell is the thing where the confusion happens. And under surprisal theory, the reasoning is that this is very plausibly a complete sentence. The horse raced past the barn is a complete sentence. So there's a much higher a priori probability that this is a complete sentence than it being something which is still to be completed. Something like the horse which was raced past the barn plus something. So probabilistically, we'd expect when we are at Hahn this to be complete. And yeah, that's under the story where the difficulty comes from. That's so fairly surprising. And what we'll do in this sort of model, we'll be explaining these things about, fact, report, and so on as similar effects that arise when memory is limited and people have to guess the context. So we'll get to this in a couple of minutes. It's all supported by word-by-word reading times, which are predicted by surprisal and broad coverage. So yeah, there are these findings where the reading time scales with the surprisal of each word. So that's good, but sort of this theory, of course, there are ways, shortcomings, and other families of models are memory-based models, which attribute difficulty to difficult retrieval and integration of representations of preceding context. And so this is, of course, very familiar to everyone in this group, but not everyone in my group. A couple of people have zoomed in, so I'll just quickly going to explain this so everyone's on the same page.
There are people here who may not know this work, so not everybody's from my lab here today. So.
Okay, great. Okay, then yeah. So if there's a question, if I'm going too fast, then anyone is welcome to just jump in and ask questions. Anyone in the audience is very welcome to jump in. Cool. Thank you for this context. Yeah, so the memory-based models assert that what's difficult is retrieving and integrating information from the past context. And maybe the most signature effects here are locality effects. So the report was surprising. There's a short distance between report and was, and that's easy. Now if we make the distance longer, if you make the distance longer, like here, ja, kannst du bitte zur Mama gehen, gell? Kannst du bitte zur Mama gehen? Kannst du bitte zur Mama gehen? So here we make the distance between the subject and the verb longer, and the verb gets harder to process. And the more we materially interpose, the harder it gets. So the more intervening, in particular, things that are somehow confusable with reports, such as other nouns, such as these here, have in orange, the more there are these intervening, the harder it gets to figure out that, say, the report is a subject belonging to was, and the harder it gets to process was. Yeah, reading times therefore elevated in the third condition because the dependency is longer. There's more intervening material that is confusing and makes it hard to retrieve the correct subject. And what we then find is these locality effects are modulated by these changes. So if you change report to fact or claim or other nouns, you get this modulation of the RT on the word was. And that part is not obviously explained by memory-based accounts. So that will be, again, what our kind of model here will be targeting. So yeah, it kind of remains open how we can really reconcile these kinds of accounts. They explain different batches of data. There are different computational implementations for models from both of these families. And I think it's fair to say that it's an open problem how we can really come up with a unified model that would do at least those things that either of these kinds of models have been convincingly shown to account for. One attempt at getting towards such a unification is lossy context surprisal, which is a sort of a version of surprisal theory that takes memory constraints into account. So this theory starts from surprisal theory, which, as I said, asserts that processing cost is given by the unpredictability. Lossy context surprisal sort of modifies this by conditioning the probabilities not on the actual context, but on a noisy representation of that context. So yeah, what this means conceptually is input is easy when it's easy to anticipate, unless the predictive information has been forgotten. or in a different view, maybe is hard to retrieve and cannot be used for prediction. So here's how this could play out for these sentences. The doctor annoyed the patient, ... And if you assume that some words are forgotten, and here I've just, stipulated that a few words will be forgotten, like that, that, and the again. Now, if this happens, of course, at this point, I'm just, stipulating that these words are forgotten. Later, we'll get a principled account of which words would be forgotten. And a rational listener or comprehender would perform Bayesian inference based on language statistics to then try to figure out what the actual sentence was. So maybe the report that the doctor annoyed the patient, or the report by the doctor, a report about the doctor, and so on. And all of these have different a priori probabilities under the statistics of the language. And they give rise to different expert predictions. So the first two are different. So the first one demands a verb to ultimately come for this to be a complete sentence. The second and third, on the other hand, cannot be continued with a verb. Instead, end of sentence would be a very plausible continuation for the second and the third version here. So this means the best that the comprehender can do in actually anticipating the next word is to average these predictions by those probabilities of those different sentences here. So you get some kind of fuzzy average prediction, which in this case is confused between maybe a verb will come next, maybe the sentence is complete and nothing will come next. That means when a verb is encountered, as it should be for this to be grammatical, surprisal will be high and difficulty is predicted to be high. So that's the basic account of this kind of locality effect that we have here in these sentences under the lossy context surprisal model, conceptually. So the idea is that this word here is hard because the sentence, due to forgetting, has been misreconstructed. There are some open questions here left open in this paper. So one question is, which part of the input would be affected by the loss? Here I just stipulated to get the right result that these three words would be forgotten. And we need some kind of more principled account of that. And the second challenge is, can we actually scale this to a broad coverage implementation so we can really make predictions on any kind of stimulus set, so we can sort of minimize subjectivity and the onus on the researcher, just the amount of labor it takes to create predictions across different experiments. Yeah, so for the first question, so Futrell et al. Looked at uniform noise, or noise that is sort of decays with distance, or increase with distance. So something like this here, where the chance of forgetting or of remembering, so red would be highly likely to be remembered, blue would be likely to be forgotten, some kind of decaying function of that. But we need some kind of more principled and explicit approach that we can actually implement. So we propose to derive a candidate model from considerations of resource rationality. So what this means is we define retention probabilities for each word at a given distance. So they are conditioned on the word and how far it's in the past, and give a probability that this word will actually be retained and brought to bear in prediction. And these are trained for a resource rational objective. So on the one hand, we want these to lead to minimization of surprisal. And to do this, we would, of course, just remember everything, because then we wouldn't forget anything and we would have the best chance of actually predicting the next word if we know the full context. So this is balanced by a constraint which bounds the number of retained words. So on average, we want to retain at most delta words. So this means we need to strategically choose which words to forget and which words to remember. So the model will tend to forget those words, if it optimizes for this, that usually are not very important for remembering, and tend to retain those that usually are important for predicting the next word. Here are some results that you get with this. So if you impose a bound of 5, so you want to, on average, remember 5 words, then only the past few words will have really high retention rates. And in particular, the content words will have higher retention rates. And the further you go back, in particular, the function words like the will have a quicker decay of the retention rates than the content words. If you retain 10 words, you get just more, but it's kind of the same pattern. And at 15, again, you get a bias towards the content words and a strong bias towards the recent words, which kind of makes sense because the content words tend to be more informative about the topic and so on, and therefore can be more useful for lexical prediction, maybe broadly speaking. And there's a recency bias because the most recent words tend to be more relevant to the immediate next words. So what we get from this model is we get an assignment of these retention rates to each word given its identity and its distance if we specify any bound on the average number of retained words. So yeah, this way we can have an answer, at least a candidate answer, to which parts of the input will actually be forgotten or affected by loss. The second question is, how can we scale to broad coverage? So we parameterize this using a neural network that computes these numbers. Yeah, it's not very important how, I guess. But yeah, it's fitted for this objective function using some machine learning tricks that convert this constrained objective function into something that you can train with the usual gradient descent methods on a large corpus. So the model is then trained. So the model is trained on Wikipedia text, and everything that I can take from there, I take from the pre-trained GPT-2 model, which means for those parts that relate to the a priori statistics of the language, we can use the more or less, at the time at least, strongest models that there are. And for some other parts we need to parameterize ourselves and train ourselves. And then in the end, we use we get the posterior from importance sampling, where we have a proposal distribution that's trained, and we then accept proposals using these GPT-2 based numbers that we get. So I'm happy to talk more about it if anyone is interested. Very happy. But I think that's sort of what's sort of the high level idea of how this is implemented in the context of getting actual predictions from it. So we have provided an answer to the two big, I would argue, desiderata of the Futrell et al. Proposal. We have an answer to which words of the input are likely to be forgotten or affected by loss, and we have a broad coverage implementation. So I think this would be a great point to ask if there's any questions. So else I'm happy to just continue, but it would be good to ensure that we're on the same page regarding the model in how it's fundamentally defined and what the intuition behind it is.
Maybe I can ask a question here. Not a question, just want to make sure I understand how the model is conceptualized. I think is it correct to say the following? So in the model, you're trying to integrate theories of prediction with theories of memory-based processing difficulties. And the way that you are doing this is that the role of memory in the story now is that it will impact your ability to make predictions. Is that right?
Yes, that's exactly right. Yes.
So what's interesting about that is that the memory literature, the people who have been completely obsessed with the role of memory in sentence processing, and that includes me, right? These kinds of people, they're actually looking at, what some people have called backward-looking events. So not anything related to prediction. So the impact of memory is not on the predictive process, but rather on the process of putting together material, that has already been processed or somehow retained in some imperfect form. So that's one that strikes me as a very different conception, Your idea strikes me as a different way to apply the role of memory in sense processing, because it's always in the service of prediction here, right? In this case, right?
That's
And
right. Yeah.
so I just wanted to say that when I read your paper, I was reading it this week again. And so one thing that struck me was that, if you think about the pure memory and sentence processing literature, there the focus is a lot on, for example, encoding interference, So you've got two items in memory and they share some features, and somehow due to some process, maybe feature percolation or feature overriding or something like that, those nouns become harder to distinguish from each other. And the key event of interest then is that when you're trying to access the correct noun at, for example, a verb or something, that's when you run into trouble. So it has absolutely nothing to do with prediction. So I was just struck by the, completely different angle that you take in this model. It's not really a question, actually.
Yes, thank
Just
you. Yeah, I agree with what you were saying. I think that's a very important point. So, and I think more broadly, this means, so here, we're sort of making the hypothesis, or, we're throwing out a model that aims to go as far as possible by attributing all the cost ultimately to the prediction failure. So when there's encoding interference in the memory component, under this kind of approach, conceptually, we will only get a downstream cost in RTs, not maybe in other measures like comprehension accuracy or so, but in RTs. We only predict, if we don't take this theory as the only component that plays into RTs, then we only predict an RT effect if there can be some kind of prediction failure attributed to this interference. And it is a very very interesting question for us. And we're also thinking about this and running this model on experimental stimuli from the literature, that everything that we can find that we can run this model on, to delineate like which kinds of interference effects that are really probably the thing of the biggest interest in the sort of memory and sentence processing literature. This kind of model can or cannot account for. And sort of here's one. So yeah, I don't want to digress too much, but the one very interesting thing which challenges us in doing that, which is that we have to base our investigation on this GPT-2 model, which is our oracle for the statistics of English. And these models themselves have some degree of interference effects in their behavior, for instance, agreement attraction. So there are some challenges to really testing this model beyond locality at this point. And we're looking at it with bigger models and so on. So we don't have a sort of clear answer at this point, but I think we will have maybe in a few months or so as to what exactly the reach of this prediction failure as the downstream cause of memory problems is, in terms of which things we can plausibly have a story for with this kind of approach, and for which ones remain where we don't have a story for it. And sort of, yeah, I don't want to digress further, but I just want to say one last thing, which is that I guess generally, if interference leads to, so I guess there's asymmetry between interference leading to facilitation and inhibition. And in similar settings, this model might predict, one but not the other, or vice versa. Yeah, I don't want to digress further, but yeah, this is a great question, and maybe we can also talk about this later if there's anything further to discuss. But yeah, I think this is a very important point about this model conceptually.
Yeah, we should talk about this. Maybe I'll write down some notes for you, because I have such a long comment that it's not worth discussing it right now. So, but I'll
Okay,
say
wonderful.
something.
Yeah, thank you so much. Yeah, I'm very, of course, very, very interested in your thinking on this. And yeah, it would be great to talk about this more. Okay, but for now I will just continue and we can get back to this. Thank you. And yeah, everyone is welcome to to just jump right in any time, even for a comprehension question, or if something strikes you in some form, or something doesn't make sense, just jump right in, everyone. Okay, great. So yeah, one prediction we get conceptually here is, so here we saw that there was a diffuse posterior, inaccurate predictions, and therefore high difficulty downstream. On the other hand, if these posteriors were more focused, we would get more accurate predictions. We should get low difficulty downstream. So what we really should be doing, we should be manipulating the sentence to change the sharpness of this posterior. So here we have the report fact contrast from the beginning. So the one thing I changed here is replacing report by fact. Now the key thing is that in statistics of English corpora, the fact has a 0.7 chance, a 70% chance of being followed by that. The report has only a 0.7%. So that's a 100-fold difference chance of being followed by that. So what this means is that the posterior is much sharper here at the bottom, and it's focused on the veridical input. So the fact that is a much better way of recovering this incomplete lossy representation than the fact of or a fact about, all of which sound really weird and are low likelihood under English language models. So we get a sharper posterior, a lower weight on these distracting non-veridical reconstructions here. And this sharper posterior will mean that we have more accurate predictions here at the bottom and reduced difficulty. So we have this this pattern here. Kannst du bitte zur Mama gehen? Gell? Wir müssen hier ein Meeting machen. Du musst aber still sein, gell? Du kannst nicht reden, während wir hier ein Meeting machen.
Wenn Rede dann du auch mit Hund.
Genau.
Und Pferdeschuh.
Genau. So yeah, we collected, used Pentry Bank and other data sets to collect as many nouns as we could that are syntactically a lot like fact or report. And there fortunately are several dozen of them. And so here is the prediction is we should get some kind of continuous change in, so we call embedding bias. We call the log P of that following the noun in the different English corpora. So this is a negative number ranging up to 0. So for fact it would be close to 0. And for report it's -5, as you can see here at the bottom. So we predict that if we increase this embedding bias, difficulty should go down, because the posterior will be focused on these radical inputs like the fact blob and so on. Kannst du bitte zur Mama gehen? Wir müssen jetzt hier ein Meeting machen. Maybe I should go somewhere. Okay. So yeah, for report that we have higher difficulty, and for fact that. So should go somewhere else. So for the fact that we have pretty lower difficulty. So yeah, the next thing is, I think, very intuitive, which is deeper embedding is rare. And also deeper embedding means there's more material that can be corrupted. So deeper embedding should create more difficulty. So that's a sort of a kind of expectation failure grounded way of thinking about locality effects in some sense. So if there's more intervening material that's syntactically complex, then corrupting some things there is more likely to lead to an incorrect prediction. And anywhere it's rarer a priori. So we should get more difficulty here when we have more embedding in this blue condition. And then third, there is the somewhat, initially I was sort of confused by this, but it's very sort of intuitive. So if you have no embedding here, the fact or report was surprising. Then if you have the fact, then because the fact is followed by that most of the time, it's unlikely to be followed by the fact was. So you get this inverse effect in the 0 embedding condition. So what we call 1 is this red condition with no embedding, just one layer of sentence. Here there is this sort of opposite effect. So it's a nice kind of control because it means we have some kind of, so it's not some kind of, difficulty of the noun spilling out into some kind of later verb, but we really have some kind of change in the direction of the effect of embedding bias when we have embedding. Okay, so this is the pattern of predictions, and surprisal theory gives us the same thing for the red condition, but it doesn't really say anything for the other conditions. In fact, more context makes predictions easier a priori. So the more you have in terms of intervening material, the easier prediction should get, and the lower the difficulty should get, therefore, even in the blue condition compared to the green condition, and which is, of course, totally non-human, but it's a prediction of surprisal theory if you take it seriously and literally. For memory-based theories, so the simplest one is DLT, dependency locality theory, where just count dependency lengths, and here the longer it gets, or the more embedding there is, the harder. And the same prediction should come out under other theories from the memory-based space. So are there any questions about this? Are we all on the same page? Is there anything that sounds is worth a question, or sounds strikes you, or is otherwise? So I'm happy to, so there's, any kind of question is totally fine.
I think I have a question. I'm not sure everyone can hear me.
Yes.
Can you speak a bit about the difference, or like the distance from the green and blue line here? Like, are those important?
So the distance between, so how large the distance is?
Yes.
So
like
at this point,
they're quite close together. In DLT, they're similar apart to as in your model.
So at this point, it's just conceptual, and no, we cannot say anything conceptually at this point about the distances, the quantitative effects here. So in fact, we don't really know whether, so here I drew the red curve as crossing blue and green, but we don't really know this at this point, just conceptually. We'll know this later when implementing the theory and looking at the actual model predictions. But the sort of here we can only say something about like the relative ordering and directions of these things, but the distances of our model predict, we need to wait for seeing the implemented results. Does this make sense, or maybe I didn't get your question right?
No, that was it. Thanks.
Okay, great. Yeah, thank you. And yeah, any question is very welcome. Cool. Yeah, seems my son found some interesting other thing to play with, so makes it easier. So yeah, now we get to the first experiment. So we have 32 items of this shape here, and we have 30 nouns that all are from this continuum that I showed, and they are either from the maximum or minimum range to maximize power and distinguishing and finding this effect, or estimating this effect. We took 56 fillers from a classic study on center embeddings, and here are the model predictions. So this answers the question that we just had. So here we have the model's predictions. So we have, so each of these little facets is one setting of the model where we vary to the average number of retained words. And we are averaging over every model run at a given average number of retained words. So each of these is a different model that was trained to do this resource rational prediction. And we have multiple runs and average over them in this plot. So what you see is, I think this is kind of worth pondering a bit. So on the right end, it's very similar to surprisal theory. So indeed, the blue most difficult condition from a human perspective gets the lowest surprisal, which means that indeed these models we take, they're GPT-2 models, they indeed are in some sense superhuman, it seems, by finding the verb after these center embeddings not confusing at all. Easier than if you just said, the fact was surprising, that they find harder than this very complicated thing with multiple embeddings. If you retain very few words, everything is lost basically, and there's almost nothing left except in the red condition, which is the easiest. And in between, you get a pattern that is conceptually like predicted. Of course, depending on how you set this parameter, you will get different patterns where sometimes the red bar is above or below the other two conditions. So we have, this effect of the red condition. We have an effect of depth where blue is above green. And we have the novel effect here is this effect of embedding bias. So that's the thing that we're really interested in, which we sort of predicting from this theory, which is the novel aspect here. And we get it in the 3 condition, the most difficult condition, in one range of higher retention rates. And when the model is sort of more forgetful, it shows it in the 2 condition, the less difficult condition also. Yeah, so this is the prediction in the center, 10 words. So I think, by now this is probably kind of intuitive. And we get these very different pictures. So surprisal theory here is just the base GPT-2 model, the surprisals we get from it. And indeed, the model finds the blue condition the easiest in terms of surprisal on this verb here. So we got RTs with the maze paradigm. I'm not sure how familiar everyone here is with the maze paradigm. So the maze paradigm is, so the way it works is for each sentence, there's a sequence of per word trials. For each word, the subject press E or I, in this case, to guess which word is the next word in the sentence. So here it can just be the, because we're at the start, so they have to press E. The only acceptable continuation is dog, so they press I. Then it's chased the squirrel. And the response times that these button presses take are the dependent variable here. They are the reading times. So the reason why we're doing this is because the maze paradigm has been showing, I think, quite consistently across different studies, a higher temporal resolution than SPR. So we've been finding it very useful for getting for rapidly getting pretty sharp sort of estimates of effects even in web-based experiments where SPR has a tendency for people to just click through and being a bit very noisy. One challenge here is, where do these incorrect words come from? So we use the technique suggested by Boyce et al., which is to use a language model to generate them and do a sort of hand manual correction phase where we check that they indeed all are impossible, or else manually replace them. And we have we're using a version where people, when they make a mistake, they're just prompted to retry. And they can just, so there is this example here where the person selected revise, and there's a prompt that's incorrect, and the person could just try again. So in the first experiment, we had 100 participants on Prolific. And we did it in a way where we had 10 critical trials per participant that were in these 3 conditions, and we had 30 fillers. And the nouns were randomly matched with the items, subject to a semantic constraint. So we would not allow things like the fact was false. And that was the point of having semantic constraints here, so that some kind of basic presuppositional anomalies would not arise. And here are the results. So we have, again, the predictions. And so what I'm plotting here is, so we ran the Bayesian Elmer on the log transformed RTs. And here I'm plotting the posterior, sort of the posterior means and the variances of this posterior for the effects for the RTs that are predicted in each of these conditions. So we have the RTs that this Elmer then fits at fact or report, and in the 3 different declared conditions. So we see that there is conceptually a very nice match to what we saw in the model. So we have an effect of depth. That's no surprise. It's a locality effect, and that's the strongest effect, of course, everywhere, because it's a very strong effect. And then across the 2 and 3 conditions, we have this fact versus report difference, which is the key novel finding here. And yeah, so so far that's sort of encouraging. We actually did find this fact versus report difference in RTs, as the model would predict we would find. And I mean, I think this lexical effect here, this effect of the embedding bias, is really sort of the most interesting experimental finding. And I'm, of course, very interested in ways in which we could get the same result using, the more typical memory-based theories. Now, I've done a lot of thinking, and I don't think I have gotten very far, but my intuitions, of course, aren't very great in how you could get this effect in, if the cost comes from, say, retrieval failures and so on. So it's a very interesting question. I also love to chat more about that. And if there's any idea just from the audience right now, or things to ask or discuss, always very happy. Okay, I'll just continue to the second experiment then. So yeah, one more prediction we can derive. So if we change annoyed to cured, then again, we get a sharper posterior, because the report by the doctor annoyed the patient sounds pretty good. The report by the doctor cured the patient is fine, but not nearly as good. So there's a clear semantic aid that we get here in figuring out what the correct sentence was. So again, we have a more accurate, less diffuse posterior here on the bottom. And we should get lower difficulty here in the second version. So we created these 2 conditions here. So compatible, by that we mean something like the report that the doctor annoyed, where annoyed is compatible with either report or doctor, and incompatible would mean, verbs, we chose verbs that are much more plausible in the context of this embedded subject than this matrix noun, which is always an abstract noun. So in the second case, it's easier to recover the dependency structure, even if something has been lost. And we can combine this with the previous prediction to get this conceptual prediction, where we have these 2 versions here, where the dotted one should be harder than the non-dotted, than the solid one. And again, so we created more items. They are fresh, different from the previous ones. And we ensured that the pre-critical word was constant across the compatible and incompatible condition. You try to change as little only in this final verb phrase. And we have 200 participants, and we now have, we are crossing these 3 conditions with this contrast here. We get these model predictions where, again, there is on the right, it's like surprisal theory, on the left, there's almost nothing. And here we get an effect of the semantic thing here over a broad range in the difficult condition. In the easy condition, the model has to be very forgetful to also show an effect there. So here's the result. So we see that indeed this annoyed versus cured contrast, the annoyed version, the semantic compatible version, where the semantics does not help in recovering the dependency structure, does have higher RTs. We can have a locality effect. We have this difference in the red condition. We replicated the effect of the embedding bias, and we got the semantic effect. We also got evidence for. So the annoyed versions create higher RTs than the cured versions. We also did, so these experiments are not our first one. So we did previous studies, after which we then fine-tuned the stimuli to eliminate some confounds and so on. So we did a meta-analysis across 747 subjects, including all the items that we created over time, including items that, of course, are somewhat potentially not as good as the final ones, but still seem fine. because we hadn't eliminated some confounds yet. So we find, the meta-analysis, we find very good evidence for the key claim. So the depth effect is, I think uncontroversial. In the one condition, that's also, that's not so important. But importantly, we even found in the simpler 2 condition clear evidence for the effect of the embedding bias. In the 3 condition, it's even stronger. And also for the semantic effect. So in the 2 condition, it's kind of borderline. We can't really be sure. But in the 3 condition, the harder one, the semantic compatibility effect is again very confident. So this is everything we have on the RT side. Are there any questions on this? Okay, one question that is open maybe at this point is, so we have seen RT effects of this embedding bias, the fact, report, claim, news, and so on difference. And we have a story of what's sort of happening in people's minds, but we don't really know whether people actually are predicting or mispredicting the way we claim they are. So as one way of getting at this, we did a production study where people got these prefixes here and then were prompted to complete them into complete English sentences. So here we have the belief that the villains were the corporate sponsors, and the task was to complete this, and almost all completions were either of the first or the second type here. So either they would produce 3 verbs or 2 verbs, and there are a few other responses, but almost all of them were easy to label into either of these types here. So what we're predicting is that people are more likely to miss a verb for the low embedding bias nouns, because there it's harder to recover the correct structure from an incomplete representation of the context. And indeed, it's what we found. So for report, story, and so on, we got about 0.7 rate of these responses with a verb missing. At fact, it was a bit lower than 0.4. We also did the same in Spanish. Here we had a somewhat different structure due to some Spanish internal reasons. So the things that are directly like the English thing didn't sound good in Spanish according to native speakers. So we did a simpler version here, the fact that the director who, and then people were just asked to continue. And again, so here we got actually very good evidence for the same phenomenon. So say, report or a story would be these words on the left, and echo on the right would be fact. In German, it's a bit less clear. It's challenging because in German these things are just easier because of the head final nature of these clauses, and the German has lots of head final clauses. So we get some evidence, but it's not very strong that there's also something the same effect in German. So these are the studies that we have in the paper, and I have a bit more of discussion. So at any point is good for jumping in. So so we asked when and why is recursive structure hard for humans to process in language? And we started from these center embeddings that are difficult. And the traditional perspective attributes this to retrieval difficulties due to intervening material. The key empirical contribution here is that we find that probabilistic cues that don't seem to have any kind of categorical interpretation, just these continuous differences from report over story to claim, news up to fact, have a big effect on the difficulty. So you get this kind of huge RT difference in the maze task between report and fact, and intermediate differences for other nouns in between. So we have this, kind of huge RT effect in some sense. And similarly for these semantic cues here, we also get a substantial RT effect, even though the structure is the same. But here we get, again, a probabilistic cue or semantic cue playing a big role in the resolution of the syntactic structure. So from the computational perspective, So and at some high level, you know, this is, of course, ties in very nicely with what retrieval-based perspectives suggest. So in computationally, the gold standard for recursion is stack or chart-based methods, and that's likely not to be what humans do. So clearly, probabilistic and semantic cues play a key role in resolving this recursion. Parsing is easy when these cues are helpful for figuring out the structure of the past, even if some words aren't, you know, brought to bear on figuring it out, have been forgotten or weren't retrieved or something like that. And parsing is hard when these cues are misleading, even though the structure is totally homomorphic, but just the words have changed a bit. So the cues are misleading when it comes to recovering the structure without full evidence. So yeah, we proposed a model of sentence parsing as resource rational prediction, and it's scaled using machine learning to arbitrary input. I think we have some convincing evidence that there's non-trivial interaction between the memory limitations and the probabilistic expectations. And the structure building is affected in some sense by probabilistic knowledge. So we get these effects here that neither surprisal theory nor DLT or other, I would argue, memory-based models can predict on their own, but by trying to unify them in some way, and here we've proposed one way in which this could be implemented, we can get these effects that neither of those perspectives individually could account for. Yeah, thank you so much.